2, 1, and let's go. So, all right, another pre-recorded lecture. Oh my god, it's getting ridiculous. This is theoretically the last one, so we'll see. But anyway, all right. So where do we leave off last time? So, get some coffee going here. Yeah. So last time we used all of our wonderful linear mapping and vector space stuff, all of that language and material and machinery that we built up to reframe solving a system of linear equations. We demonstrated that every system of linear equations is really an ax equals b, hence the first step of the how to solve it. We talked about the idea of a consistent system, so one in which b actually can be solved in terms of a times x, so in other words, b lives in the column space of the matrix A. And then we demonstrated a whole variety of things. So for just a quick refresh, the main thing that we verified, well, two things that we verified. So the first one, if we go back here for a moment, was that, where is it? There we go. Right, so having a matrix of full rank, so in other words, the rank of the matrix equaling n, so in other words, the dimension of the column space being n, then ax equals b, in fact, has a unique solution. So we're pretty happy about that. Okay, right, so again, rank was dimension of a subspace, so before we could talk about rank, we would need to have developed the idea of subspace, and then furthermore the idea of dimension, meaning that we had to get subspace, we had to get span and linear independence. And the column space, as we noted, is in fact a subspace generated by a linear mapping that matrix multiplication induces. So, right, why we had to take such a huge detour before we can come back and talk about solving systems, hopefully is now a little more clear, or at least my reasoning for doing it. Our textbook jumps to it earlier, right, without having all of the linear transform stuff at their disposal. They still have span and all that other things, so they can talk about dimension, but there's a lot about column space and rank that they want to get to that is a lot easier to handle if you have linear mappings at your disposal, which is why I decided to jump ahead. Okay. So a matrix having full rank guarantees that ax equals b has a unique solution for all elements of the column space. Pretty happy about that. And then we noted that if the rank is not full, the story is not totally hosed. If the rank is not full, so in other words, if the rank is strictly less than n, then we can find a basis for the null space that tells us what solutions are going to look like. Right, cool. And we have already seen this before, right? This is the solution to the homogeneous system, ax equals 0, and this is just some solution to the actual equation ax equals b, right? As seen right there. Well, I'm getting my ass kicked by allergies and disease. It's great. It's wonderful. All right. But yeah, so we'd already seen this form of the answer, but now we have a lot more ingredients to it, right? Specifically, we have a very clear understanding of what the solution of the homogeneous system looks like. It is just simply find a basis for the null space. Cool. And the particular solution is still just, right, anything that solves it. The existence of which we now can fully guarantee as long as B lives in the column space of the matrix. So, all right. So this is all really nice, and as we noted, now this gives you the blueprint for actually solving systems of linear equations. Really nice. Yeah, so basically you do two things. Get a basis for your null space, and then find a particular solution. Of course, this is under the auspice of a consistent system, meaning that this is actually possible. Note, this step can always be done. You can always find a basis for your null space. Null space of a matrix is just a subspace of a finite dimensional vector space, so it's got a basis. You just need to find it. This step, of course, requires the system to be consistent, which we're under the assumption of. Inconsistent systems we will handle shortly here, once we jump back to chapter 3, and we'll get to the latter part of that, where we'll talk about the Gram-Schmidt process, which will reveal how to handle an inconsistent system. Alright, cool. Alright, so yeah, basically finding the basis for the null space, will split it into two situations. The null space is trivial, meaning that you have unique solutions. As we've already proven, null space is trivial means the rank is full, and full rank guarantees unique solutions. Or the null space has a basis, and then the general solution is any linear combination thereof of these things plus the particular. Right, and that part's not surprising, because if you do A times this, that is going to equal 0. So, right, you're looking to solve AX equals B. Well, if you have anything that solves that, AP equals B, if you were to add something to P so that A times it is equal to 0, well, that would still be a solution, because you'd just be adding 0. Which, right, we specifically saw that in a proof. In particular, it was this one right here. We saw that sneaky little trick, right? And this, of course, revealing why you focus on the homogeneous first, because if you're looking at a non-homogeneous system, it's possible that homogeneous solutions are sneaking into the party and spoiling things for you. So you always need to handle AX equals 0. And again, this mirrors exactly what we did in differential equations. Solve the homogeneous first, then find a particular. Okay, so now that we got the blueprint and we've outlined kind of basically what is done, so there are basically two tasks we need to address in a lot more detail. So finding a basis for the null space and finding a particular solution. Okay. So we'll hone in on this one for the rest of these slides, and this one we'll introduce the idea of invertible matrices to solve this. So that's worth noting that you could use row operations to solve this. We'll use this as our pivot point to get to, sometimes you can actually divide over by A, and we'll talk about what that entails. But our goal for today is to focus a little bit more on, all right, how do you actually do this? And without just saying, well, row operations, well, there's a little more going on there than just do row operations. All right, so that is basically going to be the theme. So we are going to revisit row operations, and in fact, we're going to recast them as matrix multiplications. Surprise. All right, so recall the notation that we're going to use. A sub j star is what I'm going to use to represent the jth row of a matrix. There's other notations that are out there. I like this one the best. It is different from what our book does, but I like it. So I think it's a little bit more clear, in terms of what's going on. But anyway, so row operations, very surprisingly, can be rewritten as matrix multiplications, and the idea is to basically take the identity matrix and mess with its rows. Hence why we need a notation to discuss the row of a matrix. So an elementary matrix is an identity matrix that has had one row operation performed to it. So the first type, of course, is swapping rows. So an elementary matrix of type 1 will be a matrix E, so that the pth row is the qth row of the identity, the qth row is the pth row of the identity, and all other rows are held fixed. A type 2 elementary matrix is a matrix so that its jth row is a non-zero scalar multiple of the jth row of the identity, and all other rows are held fixed. And a type 3 elementary matrix will be a matrix whose qth row is the qth row of the identity matrix plus a scalar multiple of the pth row of the identity matrix, and whose other rows are held fixed. So, in other words, these are all identity matrices that have had exactly one row operation applied to them. So, for example, here is a type 1 elementary matrix. Row 1 and row 2 have been swapped. Here is a type 2. Row 1 has been scaled by pi. Because why not? Here is a type 3. Row 2 has had row 1 scaled by -2 added to it. And this right here is not elementary. This is 2 row swaps. So swapping row 1 with row 2, and then swapping row 2 with row 3. So this is not an elementary matrix. It takes more than one row operation to get here from the identity. So when we talk elementary matrix, just always keep in your mind, this is just the identity matrix. Nice missing colon right there. It's the identity matrix after one row operation has been performed to it. That's all it is. So elementary matrices, quite surprisingly, play a very important role in the world of everything with matrix multiplication, actually. And in a sense, one way to think of these things is like they're the prime numbers, right? Remember, every integer can be factored into prime numbers. We're going to see something very similar for elementary matrices. All right. Okay. So what we're doing here, and kind of what our goal is right now, is that we're going to reformulate row operations in terms of matrix multiplications. So in other words, what we're going to demonstrate here in a moment is that every row operation was secretly a matrix multiplication in disguise. And I wonder if these are precisely the matrix multiplications you need to do. Oh, look at this. Yep. All right. So indeed, if I have a matrix, remember, a type 1 row operation is swapping the rows. So here we have, given a matrix A, multiplying by a type 1 elementary matrix on the left. And again, remember, order matters at the matrix multiplication. If you multiply by a type 1 elementary matrix, now remember, this is a matrix whose identity, that's the identity matrix, after one row swap has been performed. If you multiply a matrix by that, then the action of that multiplication is precisely a normal type 1 elementary row operation, right? Where the P and Q rows of A have been swapped and all other rows are held fixed. Likewise, if you have a type 2 elementary matrix, right, so that means you've taken the identity matrix and scaled one of the rows by a non-zero scalar, multiplying a matrix by that is the same thing as doing a type 2 row operation where you scale a row by a non-zero scalar. And likewise, if you have a type 3 elementary matrix, so you've taken the identity matrix, scaled a row, and added it to another, multiplying a matrix by this performs that row operation to that matrix. So here we see multiplying A by E, and then gives me a matrix whose Q row is the Q row plus alpha times the P row, and all other rows are held fixed. Cool. Right. So all we're doing here is rewriting row operations as matrix multiplications, and this is very nice and makes proving things with row operations actually a hell of a lot easier. If you let your mind float back when we first worked row operations, there's some proofs with them. They were like super clunky. This isn't any. This is better. It's not good per se. It's better. The smell is improved. It still doesn't smell good, but it smells better than it used to. But, so yeah, so this is a really slick idea, being able to recast row operations as matrix multiplications. First of all, it should be a tantalizing idea, because as we've already seen, matrix multiplication has a lot of power behind it. Because again, it's linear transforms in disguise. But row operations, right, are kind of like a fundamental thing that we do with matrices. So having it in terms of another fundamental thing we do with matrices, very advantageous, you would think. All right. Okay, now I'm not going to torture you with this too much. I'll prove number 3 and then note that, yeah, you can do the same thing for 1 and 2. Usually when it comes to these sort of elementary matrix things, right, there's like 3 things you have to prove, like what if it's a type 1, a type 2, a type 3. And for the most part, we'll just focus on type 3, because that's the more interesting one, where you scale a row and add it to another. Swapping and scaling, I mean, that really doesn't do... It alters the matrix, of course, but it's not as drastic as the type 3 operations tend to be. And as we noted, the type 1s are really cosmetic, with some huge quotes around that. The significance of those becomes very apparent when we get to determinants, which we're getting to in chapter 4 here shortly. But the type 3 are really the more dramatic ones. So we'll usually focus our efforts on those, and if you're interested in proving the other ones, I mean, go nuts. Right. But anyway, so, all right, we'll verify now that multiplying by this elementary matrix gives us the matrix A after a type 3 row operation has been performed. Okay, so the first thing to note is that for any row that isn't the row that is getting a row scaled and added to it, nothing happens, right? Because the elementary matrix, in any of those rows where nothing is going down, you just get the identity matrix, and the identity matrix times A just gives you the original. Okay, so all of the rows that aren't the row where something interesting is happening, right, where a scalar multiple of another row is being added in, right, we get that. Nothing happens, so that's good. So indeed, that's true. So here we see multiplying by E does not change any of the rows other than the one that we're interested in. Now, in the interesting row, we have that the entries of this matrix are the qth row of the identity plus a scalar multiple of the pth row of the identity. Right, so that means since this stuff zeroes out whenever H is not P or Q, that means that the entries of E are all 0 whenever H is not P or Q. So when I look at the matrix multiplication, which again would be this summation right here, everything drops out except for when H is either P or Q, and that corresponds to picking up this term and picking up this term. And so if we look at this, E times AK, AHK, so here H, right, will run from 1 to M, and for anything that's not P or Q, it just zeroes out. So the only things we pick up are these, right, and each EJ is equal to one of these, and now what happens here when we add them up? Okay, well, first thing to note, different indices here for this identity matrix, so that zeroes out. Different identity indices here for this identity matrix, so that zeroes out. Same indices, so that's equal to 1. Same indices, so that's equal to 1, so you pick up AQK plus APK, alpha P APK, like that. So indeed, the qth row of B is the qth row of A plus alpha times the alpha times the pth row of A. So indeed, multiplying by this elementary matrix performs the type 3 row operation. Beautiful. Cool. All right. So there you go. So as I noted, right, this is a great example of a proof that's not hard per se, but there's a lot of indices flying around. So there's, right, you're keeping track of your minding, your P's, and your Q's. So, and this is a little bit of a harbinger of things to come. There are going to be some proofs down the line here that we're going to do that are serious index management sort of things, especially when we get to the exciting world of determinants. A lot of the proofs that you'll see there are going to basically look like stuff like this. So they're not awful, but there's management that needs to be done. A bookkeeping type proof, if you will. So, all right, nice. Okay, so like I said, I did this for a type 3 row operation. You can do it for type 1 and type 2. The type 3, though, are the ones that are a bit more involved, so it's worth doing those proofs. And then noting that the other ones aren't too awful. Row swaps sometimes can be a bit of a pain in the ass, actually. You might see that. But these are definitely the heaviest lifting, because there's a lot more running around. All right, cool. All right, so there we go. So now we have recast elementary row operations in terms of matrix multiplication. Specifically, multiplying by an elementary matrix performs row operations. So row operations now can be represented as matrix multiplications. That's very nice for a variety of reasons. And one of the neat things about elementary row operations was that we could undo them. So if you let your mind flow back, we verified that, yeah, a row operation, when performed, can always be undone. So that means if you've got an elementary matrix, you can always find another one so that the product is equal to the identity. That makes a lot of sense because multiplying by the identity matrix does nothing. So if you multiply by E performing a row operation, then there should be another elementary matrix out there so that the row operation, when applied, gets the matrix back to normal. So in other words, by associativity, this multiplication better be the identity. Okay. All right, and similarly to the proof we just did, I'll do it for type 3, and then if you're interested, you can do it for the other types. Okay. All right, so let's let P and Q be the rows that we're going to use for the type 3ing. So in other words, I will scale P by alpha and add it to Q. All right, so I'll let L then be the type 3 matrix that scales P by negative alpha and adds it to Q. So undoing the action of scaling by alpha, scaling row P by alpha and adding it to row Q. So we multiply these together and look at them. So the Qth row, as we've already proven, multiplying by L, the Qth row will be the Qth row of the matrix that's being multiplied, plus negative alpha times the Pth row, but the way E is set up is that its Qth row is the Qth row of the identity plus a scalar multiple of the Pth row, and the Pth row is held fixed. So hey, they cancel out and we get the Qth row of the identity. And of course the H row of L times E. So remember, multiplying by this performs the type 3 row operation, but the row that I'm interested in is the row where nothing is happening, so you just get the H row of E. E is a type 3 as well, so the H row doesn't have anything going on, so you get the H row of the identity. So the rows of this are precisely the rows of the identity matrix, so they must be equal. Very nice. So there we go. Elementary matrices undo each other. Quite cool. Right, and again, we expected this because we've already discussed that row operations can always be undone. Right, and that was part of the key ingredient of the proof that if you have a set of solutions to a system of linear equations, row operations do not change the set of solutions. All right, so here we now have it written in terms of matrix multiplications that if you have a row operation, you can always find another row operation that will undo its action. Cool. And therefore, there you go. All right. So now that we have row operations defined in terms of matrix multiplication, we will now define the idea of row equivalence. And row equivalence is the following. Given matrices A and B, we'll say that A is row equivalent to B if I can multiply by a finite number of elementary matrices on the left to turn A into B. Or in other words, A can be turned into B via a finite number of row operations. Okay. So we've already seen equivalence relations on display when we were talking about linear isomorphisms, right? And the idea there was that that classifies all vector spaces. It gives you a tool to go, these two vector spaces are the same thing, and that is precisely what row equivalence here is. This gives us a way of classifying matrices. This lets us say, okay, these matrices are row equivalent, so they're basically the same thing. Yes.
Pause?
No.
You just pause?
It breaks the video into two parts. Waiting it.
What? You want to interrupt your class?
What?
I don't want to interrupt.
Okay.
How much longer?
Like 20 minutes.
Okay.
Alright. Alright. Alright, let's get back to it. Good time to pause the video there. Okay. Yeah. Alright, so yeah. So just like linear isomorphisms let us classify the realm of vector spaces by going like, okay, if you have a linear isomorphism from this vector space to that one, they're the same thing. Row equivalence will play the same role, and in fact will prove the same three things. Every matrix is row equivalent to itself. If a matrix is row equivalent to another one, then we can go backwards. And if A is row equivalent to B and B is row equivalent to C, then we can jump from A to C. Okay. And again, note that point 2 lets us use the phrase A and B are row equivalent without that being problematic. Right, and especially with row equivalence, we need to be really careful that this is meaningful because row equivalence is multiplying on the left by elementary matrices. Right, so the multiplication must occur on the left, right? So, and again, right, the row operations were multiplications on the left, right? There's no way of getting this to work by multiplying on the right. Actually, if you tried multiplying on the right, what you would get are like column operations, which is like a silly thing to ask. You'd be like, oh yeah, can you do like column operations? And you technically can, but what you're really doing are row operations to the transpose, so it's not really that interesting. So, but it is a thought, I guess. But anyway. Alright, let's get into this. So, 3 things to prove. Every matrix is row equivalent to itself. If you've got a matrix equivalent to 1, then we can reverse it. And then we can jump from one matrix to another matrix, and then you could skip the middleman and go from A to C. Alright, so hopefully you notice something. The identity matrix is in fact an elementary one. In fact, it is representable as a couple of different types. You can represent it as a type 2 by scaling one of the rows by 1. That works. You can also represent it as a type 3 by scaling by 0 and adding it to a row so you don't do anything. So there's a couple of ways of doing it. But it's an elementary matrix, so there you go. A is row equivalent to itself, just multiplied by the identity. So in other words, to perform a row operation, that doesn't actually do anything, right? And our rules for that do allow this to happen. All right. Okay, so now let's say A is row equivalent to B. That means there are elementary matrices that, when multiplied on the left, give you A, transform A into B. So there's a finite number of row operations that turn A into B. All right, as we just proved, you can always undo elementary matrices. You can always undo row operations. And so multiplying all of those on the left here will get rid of this, because you'll just pick up the identity matrix, but you'll pick those up on the left of B. So now we have that B is row equivalent to A. All right. And for A is equivalent to C, provided that A is equivalent to B and B is equivalent to C, well, right, our hypothesis guarantees that I can multiply A on the left by some matrices to get to B, and I can multiply B on the left by some matrices to get to C. So multiply these, then multiply those, and there you go, you get to C. So A is row equivalent to C. All right, so this defines now a nice equivalence relation on the set of matrices via row operations. And again, we have now proven that row operations can be written in terms of matrix multiplications. So, yay, pretty happy about all this stuff. Okay. Okay, so naturally now you want to start asking, okay, well, what does this got to do with, like, solving systems of linear equations, which is, right, again, what we're talking about right now. All right. So we can bring that around and actually get there by pointing out that there's something elementary matrices do with respect to the null space. And that is, they don't change the null space. So now it comes into light exactly why row operations play a very powerful role role in actually solving systems. So we've already seen that you can use them to solve it, right? But the proofs there were left a little bit to be desired, and now we're going to start seeing how you can actually use that to help us out here. So specifically, we will now prove that the null space of a matrix does not change after a row operation has been applied. Okay, and of course, remember, every row operation is just a matrix multiplication now. All right, this is actually super easy to prove. Let's say you've got something in the null space. That means A times X is equal to 0. Multiply by your elementary matrix. Matrix multiplication is associative, so I can move the parentheses over. That's equal to 0, so we get 0, and we're done. So if you're in the null space of A, you're in the null space of E times A. It's in the game. Yeah. So, right, and again, EA here is just A after a row operation has been performed. Okay, now the reverse inclusion is the more interesting one here, right? Obviously, there was nothing special about E being an elementary matrix. In fact, this is what I've proven here would work for any matrix, so it's not particularly interesting. Okay, now the reverse is the one that's actually going to have something going on with it. So if X is in the null space of this, that means that E times A multiplying X gives me 0, because X is in the null space. All right. Now, every elementary matrix can be undone by a matrix multiplication. Right. Again, every row operation can always be reversed. You can always undo a row operation after you do it. Row operations are not permanent destruction of your matrix. You can always undo them. So, let L be the row operation that undoes the row operation E. Then A times X is the same thing as the identity times A times X, which is L times E. Matrix multiplication is associative, so I can move the parentheses around. This we know by hypothesis is 0. Anything times 0 is 0. So there we go. X must belong to the null space. There we go. Now we see proving that this is a subspace, a subset, not space. Proving that this is a subset of that actually used the fact that E was elementary. The forward direction did not. So again, that is something to always be on the lookout for in a proof where if something is hypothesized but didn't actually show up. So it does show up right here. So the proof's good. Alright, so now we see that your null space is unaffected by row operations. So that's really nice. Because in fact now we can push that even further. If you have row equivalent matrices, then their null spaces must be the same, and furthermore, their ranks must be the same. Ooh, that's pretty exciting. Okay. So, point 2, hopefully you can kind of see will immediately pop out of point 1, but let's prove point 1 first. So by hypothesis, A can be gotten to B by multiplying by some elementary matrices. All right, so just do a finite number of row operations, then A will turn into B. All right, as we proved, multiplying by elementary matrices does not affect your null space. So B is equal to the null space of A times all this junk, but each one of these multiplications will not change your null space. So you can start throwing them out, and you can keep throwing them out until you get rid of all of them. So we'll get the null space of A as the null space of B. All right, now this tells us that the rank of two row equivalent matrices must be the same by the rank nullity theorem. We know the rank of A plus the dimension of the null space of A is the number of columns of the matrix. B has the same number of columns, so its rank plus the dimension of its null space must also equal n. But by 1, we know that the null space of B is the null space of A, so we can subtract them off and then get that the ranks are the same. Nice. So note, this reveals something to us. We've already talked about the rank dictating does AX equal B actually have unique solutions or not. Here we now see row operations, when applied, the rank doesn't change. So if you want to solve, do row operations to your matrix. Makes your life a lot easier. Now we see that the row operations, right, these are preserving the very structures that we're imposing on matrices, so it's nice. Okay. So, equipped with this, right, it's worth now discussing something we already talked about with row equivalence, which is, given a matrix, you can always perform enough row operations to it to get it into echelon form. And just to clarify what that means, so the main thing is that the first non-zero entry of a row is always strictly to the left of any non-zero entry to any row below it. So there is the nice staircase pattern going down. So something that I had mentioned was that the other thing that people usually throw in is that all the rows of zeros are at the bottom. And when I first talked about it, I was like, yeah, you can do that. Who cares? But when I was working on these slides, I realized, oh no, there's actually exactly one spot where you actually need that condition. So I remember when I was like first talking about it, I'm like, I guess you can do it. But no, yeah, you really need to do it. There is a proof that we're about to do in a moment where you need all the zero rows to be on the bottom, otherwise the proof gets janky. So in other words, then these things right here are nice in echelon form. Here we see the staircase pattern going down. Column zeros, that's fine, who cares, right? The main thing being that the leading entry in each row is always strictly to the left of any leading entry in the next row. And then any row of zeros is down at the bottom. So these things are not echelon form, even though this one has the staircase pattern. I want the zero rows in the bottom, which again will become clearer in a proof that we're going to get to. And here, obviously, we lose the staircase pattern, so this is definitely not echelon form. And as we noted, every matrix can be made to be in echelon form via row operations. So that means in our new language that every matrix is row equivalent to A1 in echelon form. Cool. All right. Okay, so we noted, and as we saw in practice, getting a matrix in echelon form is really nice because in echelon form, you can usually just backsolve, or it reveals that backsolving is not possible. So, for example, finding the null space of a matrix in echelon form is super easy to do. So, for example, here is a matrix in echelon form. If I want its null space, well, all right, anything in the null space would satisfy this matrix multiplication. And then, like I said, you just backsolve. And then from there, you can verify that this is the basis for the null space. So, right, the first step in solving AX equals B is always to find a basis for your null space. And as we've proven, any matrix A that you have can be made an echelon matrix via row operations, and as we proved, null spaces are unaffected by row operations. So if you actually want to find a basis for your null space for your matrix, which you're going to be asked to do on your homework, just perform row operations, get an echelon form, and then find the basis for that. The basis you find there must be a basis for the null space. So that is really nice. Like, this is a way of actually performing the first step to solving AX equals B. To solve any system of linear equations, take your matrix, echelon it, get a basis for the null space. Right? Because in echelon form, you just simply backsolve, and that gives you the basis for free. So, yeah, that's really nice. Alright, so what's up next then? Alright, that kind of finishes it off, right? Well, not quite, because there's actually a little bit more to the story than just do echelon form, then get your basis for your null space, and then kind of wash your hands of it. So, if you let your mind float back, I talked about this idea of the fundamental subspaces associated with a matrix. So given a matrix, there are two fundamental subspaces. It's column space and it's null space, and we see them on display in the rank nullity theorem. And I said when we got to those two fundamental subspaces that technically there are four fundamental subspaces. The other two are just the transpose of the matrix, the column space thereof and the null space thereof. So one of them that's worth discussing now, because we're basically in position to perfectly talk about and prove everything you'd ever want to prove about it, so let's do it. So similar to the column space, the row space is the span of the rows. So hopefully it's not surprising that this is the thing, because, well, column space was the thing, so it stands to reason the row space was the thing. But as we're going to see here in a brief moment, the row space is really a column space in disguise. So when it comes to the fundamental subspaces associated with a matrix, the column space, the row space, and the null space are basically the ones you care about. There is the fourth one, but very similar to the big four of thrash metal. You've got, you got your Slayer, your Metallica, and your Megadeth, your column space, your row space, and your null space. Did I line those up right in my head? Well, of my particular favorite ones. Yeah, Slayer is definitely the row space, the one that's just like, yeah, it's there, I guess. And Megadeth is definitely the null space, the best one. Yeah, there's that fourth one where it's like, I guess Anthrax shows up, but maybe it really should be Testament or like Death Angel. Yeah, there's plenty of other bands that should be number 4. Exodus probably is, the thrash metal's dumb anyway. Why am I talking about this? But anyway. Alright. So, row space. Yeah, what's this about? Well, it's the span of the rows. So, like I said, we've kind of got an answer on, okay, I want to get a basis for my null space, because that's what I want to do if I want to solve Ax equals B. Right, it turns out there's a little bit more to dig into here, and so that's what we're going to start doing now, and not finish, because we're already at the 42-minute mark. Okay, so if you have two matrices and a row equivalent, then the row spaces are the same. That's nice. And as always, I will prove a simplistic case of it, and then note that if you want to do the full-out proof, you can go ahead and do it. So we'll do the case where it's just one row operation, and the row operation is a type 3 operation. Okay. So indeed, if I have a type 3 row operation going down, so where I've got P and Q and a scalar for my row operation. Okay. Right. Well, if you were to look at an element of the row space of EA, it would be a linear combination of the rows of EA. But if you look at the rows of EA, all of the rows are the same as the rows of A, except for one where it's a linear combination of the rows of A. So this just gets subsumed into the linear combo here, and you just get a linear combination of the rows of A. So there you go. Anything that's a linear combination of the rows of EA is a linear combination of the rows of A, so the spans are the same, thus the row spaces are the same. So that's generally how the argument goes down for the other row operations. Any linear combination of rows of E times A is just a linear combination of the rows of A in disguise. Either I swap locations, I scaled one of them so the scalar can get sucked into one of these outside scalar multiplications, or for the type 3, which is the one that's a little bit more involved, one of the rows is a linear combo itself, and then, hey, that stupid linear combination is a linear combination lemma the book was going on about applies. There you go. Cool. Alright. So there we go. We now have that if you've got row equivalent matrices, the row spaces are the same. Now, naturally asking, hopefully, going in that, all right, how does this relate to everything? All right, well, let's start moving in that direction. So the first thing we'll note is that the row space of your matrix is simply the column space of your transpose. That hopefully isn't shocking. The transpose of a matrix is just replace the rows with the columns. So the row space of your matrix should just be the column space of the transpose. All right, it's super easy to prove this because if we were to look at the jth column of the transpose of your matrix, that gives you the kth entry of that is the kth entry of the jth row. So that means all of the elements of the row space, which are these rows of your matrix A, each one of these rows is just the column of the transpose. And as we proved, the column space is the span of the columns. So there you go. So there we go. So this other fundamental subspace is really just the usual two fundamental subspaces of a matrix, the column space and the null space, but now just being applied to the transpose. So the column space of the transpose is the row space of the original matrix. The null space of a transpose, I've never seen that given an interesting name or anything like that. It's just like, it's that thing. I'm sure somebody's got a goofy name for it, but we're not going to touch it. It doesn't really end up being too exciting for our purposes. But it's out there. It's a thing. People care about it. But yeah. All right. So next up, we will now prove something very amazing about the connection of the row space with the column space, which is that they have to have the same dimension. And that hopefully that is a shocking sounding result, right? The column space, which is the span of the columns, and the row space, which is the span of the rows, always have the same dimension. Even though the number of rows and the number of columns can be completely different, the dimension of the subspaces that they create are always the same. That is, how the hell is that true? Right, that on face value should be a no fucking way. Like, that just sounds so ridiculous. But it is. It's true. It's probably one of the most striking results you'll ever see. Right, because look, you could have like one column and 12 billion rows, but it's like, yeah, no, the number of things that example is a little too extreme. Like 12 billion and 14 billion columns and rows. It's like somehow the dimensions line up. It's really bizarre. And this is another one of those results that set me off on this path different from the book. The book has the proof of this, and oh my god, every book in existence tries to prove this in the most ridiculous way possible. And again, this is why I jumped over to matrix multiplication first. So this is a very fundamental result, this idea that the dimension of the column space is the same as the dimension of the row space. I don't think it has an official name other than row rank is equal to column rank, which is usually how it's stated. Every single book in existence in linear algebra, except for one, every single book has a proof of this that is just complete insanity and impossible to read. Except for one, Linear Algebra Done Right, which is not the book we're using, which is also a book that's got a bunch of problems with it because the person who wrote it's an insane person. But one of the things they have is a proof of the column rank is equal to the row rank. That is really nice and natural and very obvious. And the proof requires matrix multiplication. And that's it. So this is a very important and classic theorem of linear algebra, that the row space and the column space have the same dimension. The implications of that on solving systems is going to become a little bit more apparent. We will return to echelon form, and we'll see that the dimension of the row space and dimension of the column space lining up has some serious consequences in terms of what happens after you do get your matrix in echelon form. So this is wrapping around everything. This isn't just a random divergence. But yeah, so every linear algebra book has to prove this, and only one of them has a proof that isn't like complete garbage. And that's the one I'm about to show you, where you just need to know matrix multiplication, which is why I severely disagree with how our book approaches it because, again, they get to matrix multiplication after they do rank, and it's like, no, if you've got multiplication, you could prove this thing for rank, which you want to prove, and it comes out super nice. So let's talk about this proof then. All right. So we're going to prove that the rank of a matrix does not exceed the dimension of the row space. Okay. So the first thing to note is that if A is equal to 0, then all of the rows are 0. So the span of the row space is just the trivial vector space. Right, because the smallest subspace containing this is itself. It is itself a subspace, so that's not surprising. And right, if your matrix is equal to 0, then right, your rank is 0. So here you go. The rank is equal to 0, which is the dimension of your row space. All right, so the more interesting thing is, let's say that we've got A is not equal to 0. Then there's some row that's non-zero, so the dimension of the row space is at least 1. Okay, lock down a basis for this thing. So that means that for each element of the row space, I can find a collection of scalars so that the jth row is a linear combination of these things. Right. Sorry, the row space is the span of the rows, so each one of these things is in the row space. This is a basis for the row space, so each one of these is a linear combination thereof. And, oh, hey, wouldn't you know it, from 1 to m, I can find p scalars, so I can create a matrix by just choosing these scalars. And furthermore, I can make a p by n matrix by taking the basis I got here and just making those the columns. So in other words, the kth column of B is the B sub k. Yeah. No, the other way around. The rows. Yeah. Come out of the row. Yeah, the H row of B is the H row of is just B sub H. So hey, C here, linear combination, columns, so you've got a linear combination thereof. So note now, if we were to look at the jth kth entry of A, the jth row of A is a linear combination of those vectors, and if you look at the kth entry of those, hey, this is the first entry, right, so the B's form the rows of the matrix capital B, so the kth entry here would just be 1k, the kth entry here would be bk, and hey, when you know it, you've got matrix multiplication. So A now can be written as the product of C times B. That's not too surprising, right? What's the trick that I pulled, right? The linear combination, right, was set up to turn into a dot product, which is what matrix multiplication is built off of. So what does this mean? So that means that for each k, the kth column, which of A would be the kth column of this matrix multiplication. So now the kth column of a matrix multiplication is a linear combination of the columns of the matrix on the left. So hey, that means each element of A's column space is a linear combination of these columns from C1 to CP. So that means the column space lives in the span of these columns of C. And note, column space is contained in a set that has been spanned by P things. So Steinace's exchange guarantees that the number of linearly independent things in here cannot exceed P. So the rank of A, which is the dimension of its column space, cannot exceed P. And P came from a basis for the row space. So there we go. The dimension of the row space does not exceed the rank. Beautiful, elegant, amazing proof of this fact that the rank never exceeds the dimension of the row space, right? So the trick was to fix a basis for the row space, Every row is a linear combination thereof, and those linear combinations give rise to a matrix multiplication, so that A is actually equal to the matrix multiplication, and matrix multiplication can be thought of as a linear combination of columns, because again, they're dot products, and as we've already discussed, dot product is built into matrix multiplication. Okay, and then Steinitz exchange comes to save the day and give us that very nice result, so we're pretty happy about that. So there we go. All right, a really neat, elegant proof that only uses matrix multiplication. It's so much better than the garbage your book tries to pull, so if you want to see what the book does versus this, trust me, this is better. All right. So now, furthermore, right, we proved now that the rank of a matrix does not exceed the dimension of the row space. In fact, they have to be equal, as I've already noted. And here's where we'll end, because I already hit 55 minutes. This is not too hard to verify. So we already know the rank does not exceed the dimension of the row space. And what do we know about the row space? Well, it's the column space of A transpose. Okay, well, hey, that's the rank of A transpose. That has to be less than or equal to the dimension of the row space of A transpose, which has to be the column space of A transpose transpose, but two transposes get you back to normal. So there we go, the dimension of the row space does not exceed rank, so they must equal each other. And there we go, we have now verified that the dimension of your column space is always equal to the dimension of your row space. So another way this is said is that row rank and column rank are actually equal. And equipped with this now, we're going to be able to say some more things about echelon form of your matrix and get a few more things about when you're finding your basis for your null space. What are some tricks of the trade you can do to get it? Right. So, right, we'll see that next time, and yeah, and hopefully that will be, and next time will be Thursday, and that will hopefully be, again, a live lecture. It should be a live lecture. Everything should more or less get back to normal here by Thursday, so, all right, I will see you then.